So welcome to our April 2025 online lessons. So we talked about Bonaba cycles just briefly. We'll continue to explore the energy changes that take place in Bonaba cycles. We also briefly outlined Hess law, but we'll come back to Hess law as we continue to talk about energy changes. We'll talk about Hess cycle diagrams. But there was a question raised which made me think I have to go back to this basic concept. What is enthalpy? So let's begin where it all begins. What is enthalpy? So when a chemical reaction occurs, there is normally a change in energy. The enthalpy change of a reaction is the heat change. So basically, enthalpy changes are about heat changes in a reaction at constant pressure. So it is given the symbol delta H and as units kilojoules per mole. So when we talk about energy changes, when we measure energy changes in chemical reactions, we use kilojoules per mole. That is our standard unit. So that is your delta, that small triangle. It simply means change in. So this is the change in enthalpy. Okay. So that other symbol that is called that symbol means substance was in standard state under standard conditions. So that circle with that line denotes that it was done under standard state and in standard conditions. Standard conditions are 100 kilopascals pressure and 25 degrees Celsius or 298 Kelvin in terms of temperature. Okay. And then these are basic words. We were using them, but I think we should understand what they really mean. So, reactions can give out heat energy or they can take in heat energy. Endothermic reactions, these are reactions that absorb energy from the surroundings. So that would be the energy profile diagram. So here you see that we have reactants at a lower energy level. This is the energy level showing on our y-axis. This is time or the progress of the reaction. So starting off here, we have our reactants at a lower energy level. And when they absorb heat energy from the surroundings, they then form products that are at a higher energy level. So our enthalpy change is positive, meaning that we have taken in heat energy plus energy. We are adding energy to our reactants to form products that are at a higher energy level. So these are endothermic reactions, and this is the typical energy profile diagram. We can also highlight activation energy, which is the amount of energy that is required to kickstart your reaction. So you can see here that this is representing our activation energy. So let's look at an example there. The thermal decomposition of calcium carbonate. So we'll talk about the thermal decomposition of these carbonates later on. But this is just an example where you can heat your calcium carbonate to produce calcium oxide and carbon dioxide gas. So you can see here that the enthalpy change is what? Positive, meaning that we take in energy. So that's an example there of an endothermic reaction. Exothermic reactions are reactions that release energy to the surroundings. The typical energy profile diagram looks like that. And we have reactants at a higher energy level than the product. So it means that the reactants have to lose energy to form products that are at a lower energy level. So in that case, our enthalpy change becomes negative. In other words, it's minus energy. We are releasing energy into the environment, and we can indicate our activation energy there using that green arrow. So here the green arrow was from the reactants to the peak of this line here. Same here, from the reactants to the peak. This is where you find your activation energy. Okay, let's move on to talk about an example here. This would be combustion of this is ethane. Combustion of ethane is an example of an exothermic reaction that releases heat. So this combustion produces water and carbon dioxide. All right, so let's move on. So there are 6 types of enthalpy changes, and we looked at some of them in the previous video. the standard enthalpy change of reaction. So this is an addition to the list that we explored. So there is the standard enthalpy change of reaction, which is the enthalpy change of a reaction according to the molar quantities in the equation under standard conditions. So when you see this delta on R and our H there, and this symbol here, it means that we are talking about the standard enthalpy change of a specific reaction. All right, then we can have our standard enthalpy change of neutralization, which is the enthalpy change when an acid and an alkali react to form 1 mole of water under standard conditions. Standard enthalpy change of combustion, enthalpy change when 1 mole of a substance is completely burned in oxygen to make carbon dioxide and water under standard conditions. Okay, standard enthalpy change of formation. So remember, once we put this, it denotes standard states and conditions. Standard enthalpy change of formation, this is the enthalpy change when 1 mole of a compound is formed from its element in their standard states under standard conditions. We looked at this in the previous video. So generally, bonds are broken and made during a reaction. You must know this. And bonds broken, so to break a bond, you need energy. For you to be able to break a bond, you need energy. So that means this is an endothermic process and the enthalpy change is positive. So as we saw earlier on, the typical energy profile diagram for an endothermic reaction is that you have reactants at a lower energy level and products at a higher energy. So if more energy is needed to break bonds than the energy given out when bonds are formed, the reaction is exothermic. It's important to know that we have to compare each time a reaction takes place. We have to compare the amount of energy that was needed to break the bonds and the amount of energy that was released when new bonds are formed. So the formula generally is that the enthalpy change for a reaction is going to be equal to your the total energy that was needed to break bonds minus the total energy that was released when new bonds are formed. So here, when bonds are formed, energy is released. So this would be according to this typical energy profile diagram showing there. So if more energy is released when bonds are formed than what was needed to break the bonds, then the overall reaction will be exothermic. So it's important for you to remember that it's a comparison. So mean bond enthalpy, what is this? Bonds of the same type don't all have the same amount of energy. For example, here there are 4 carbon hydrogen bonds in methane, or with slightly different bond energies. The energy needed to break the first carbon hydrogen bond will be different to the energy needed to break the second, and on. So we can measure the enthalpy of breaking all 4 bonds and divide by 4 to get an average bond. So the mean bond enthalpy, this is the average amount of energy that is needed to break a specific bond. So, for example, here the total would be 1662 of all the 4 C to H bonds in CH4. The average becomes 1662 divided by 4, which is 415.5 kilojoules per mole. So this is the concept of mean bond enthalpy, and you'll be given these values in your data booklets. Even the questions that require for you to use this will give you the mean bond enthalpies for specific bonds. Okay, so enthalpy change is using mean bond enthalpy. So the enthalpy change will be, like we said, the total energy needed to break bonds minus the total energy released in forming bonds. To calculate energy change for combustion of methane, here's what we need. We need the table showing us the mean bond enthalpies for all the bonds that are involved there. We have our carbon to oxygen double bond 805, carbon to hydrogen 435, oxygen double bond with 498, oxygen to hydrogen 464. So we now need to think what bonds are we breaking to our left side of the equation here. So we have a CH4 methane, so we have a total of 4 carbon to hydrogen bonds. So this is what's showing here, 4 times our mean bond enthalpy 435, we get 1740, and we have 2 moles of oxygen to oxygen double bond, 2 times our 498, which gives us 996, and the total energy that was required to break these bonds to our left of this equation is 2736 kilojoules per mole. So this is the endothermic process, the bond breaking process. Let's talk now about the right hand side of this equation, where we have our carbon dioxide and 2 moles of water forming. So how many bonds are formed there, and what is the total energy that was released when these new bonds were formed? So for carbon dioxide, what we have this bond here, carbon to oxygen bond, and we have 2 of those in carbon dioxide. If you look at the carbon dioxide molecule, it is 2 of those bonds. So 2 times 805, 1610, and we have our water, which is these O2H bonds, 2 of them, right? So we have 2 in each water molecule. However, we have 2 molecules of water, so we have a total of 4 O2H bonds. So 4 times our 464 to give us 1856, and if we add there, we get a total of 3466 kilojoules per mole. So now the comparison, let's now plug this into this equation here. The total energy needed to break bonds was our 2736 minus the total energy that was released when we formed new bonds there, which is our 3466, and we get so when we make that comparison, we get a negative enthalpy of 730, meaning that the overall energy change is exothermic.